So we did the YDSE, right?
Yes, sir.
Yeah. Now in YDSE, there are many formats, like many modification actually, you can say. So in the last,
Sir?
just
Okay, sir.
in the last derivation, the source from which the light emanated was kept symmetrical with respect to the two slits, right?
Yes, sir.
So now what will happen if we keep the source asymmetrically? Now, no matter what I draw here, you have to imagine that the scale used, the dimension used are very small, and therefore you're eligible to apply the rules of approximation in most of the calculation. Before I move to the modification, I'll show you how to find the path difference once again. You can see clearly that the two slits are symmetrical. If you really want to find the path difference without using any trigonometry, just using the basic Pythagoras, we can also find the same. So this distance we call capital D and this is called small d. So this is d by 2 and this is d by 2. And while traveling from S to S1 or S to S2, there is no path difference. So we can totally ignore the path up to which we see no difference. So the path difference will come up because of the S1P and S2P, right? SS1 and SS2 will not contribute to the path difference, isn't it?
Yes, sir.
All right. And now what you can do next is you can draw a line parallel to the central line. So if you say that this position is at a distance of y, from the center of the screen, you can call y.
Sir, when you say S1, S2, like does S1, S2 distance does not contribute to the path difference, you mean like directly?
I mean, yeah. So if you, because the source is here, so whatever wave will start traveling from the source up to S1, S2, there is no difference, isn't it? So
Yes.
S2, S1 and S2, S2 is equal path, so they will contain equal number of wavelengths, isn't it?
Yes, sir.
So the number of wavelength up to S1 and up to S2 is same.
Yes, sir.
But now if you move from S1 to P and S2 to P, you are traveling different distance, therefore you will be containing different number of wavelengths, isn't it?
Yes, sir.
Okay. So now what we are going to do is we are going to find the path difference, but in a slightly different way. So the way of writing is S2P minus S1P, and S2P you can write as y1 plus d by 2 whole square plus d square. Do you realize this?
Yes.
And S1P will be how much?
Minus d by 2 whole square plus d square.
So this way of a derivation is also required. I mean, one should know. And I had shown you the only one way, like trigonometric, which is easier definitely. And now
Yes.
capital D is very big. Always remember that capital D is really big. YN and the D all are very small. Okay. And
Yes.
therefore, I mean, see, the entire setup is done in such a way that D is in meters. So imagine D in meters and YN will be in millimeter. Okay. So technically everything is close to the O only. So technically the theta is not much. Okay.
Yes, sir.
Now to make this easy, we can take the D square outside. So what I get is YN by capital D plus D by 2D whole square, right?
Yes,
Minus same thing here, capital D and then 1 plus YN minus D by 2D by D whole square. And now we can use the binomial approximation. So we can add as 1 plus 1 by 2 times. And then we have YN plus D by 2 by D. You can write like this also. This is whole square, right? And minus same thing. Now further you can see that something gets cancelled. So what you're left with is D gets cancelled, then 1 by 2 D square and 1 by 2 D. And okay. So eventually you're left with this much, right?
yes, sir.
And now A square minus B square we can write as A plus B. So if you add A and B, what you'll get is 2YN. Or you can simply say it's a 4AB, right?
Yes, sir.
So I can add 4A into B. And you can see it is coming out to be same answer, Y and D by 10. So after solving, the path difference is D times YN by D. And this YN by D, sorry. Yeah, this one. So this Y1 by D was the tan theta. And that we wrote from actually sin theta. For a small angle approximation, sin theta and tan theta we can convert, right?
Yes, sir.
So this is the reverse derivation. The first derivation was we were using this directly. And now this is the actual way of derivation. So whenever you come across a situation in which you don't see the standard YDSE, you have to go through the basic derivation scale. So this was just for that purpose, so that you can know that how to derive. Now, we'll see the next part that's called the effect of shifting of source. Effect of shifting of source. Okay. Now imagine if we have YDSE. See, the maximum minima rules remain same. The path reference n lambda and for the regular case. Okay. Until we are not playing with the medium, you can always use the maximum minima condition directly. The moment medium will come into picture, we have to do it from scratch. So we'll make some changes there.
Okay, sir.
Now what happens if I shift the source slightly above the? Okay, now you will be wondering. So now I need to mention the, let's say this is D dash. And this is our regular D. I will not change the D. And now we have a string. Now, you know how much is D naught by the way? Can you guess the D naught value?
Sir, it's greater than D by 2. As in,
Yeah, so it is in millimeter. So we
Oh,
are
as
shifting by
in
millimeter,
orders
right?
of.
In fact, D naught is also in millimeter.
Okay, sir. Yes, sir.
No. The light now source is here. So the way light will travel is S1. And we always take the point P above. I mean, see, you can take anywhere, but this is like a very convenient way of assumption so that we can do the derivation with ease.
Okay, sir.
So we always construct the path like this. Now, if you remember earlier, the S1 and SS2 was not creating any path difference, isn't it?
Yes, sir.
But now even that will create the difference, right?
Yes, sir.
So we have to draw the angle on both sides like this. So if I call this angle as alpha, because this we call theta by default. So now I have to also call alpha. Okay. Now the path difference here, you can draw a perpendicular. So on the left, the path difference is up to here. You can just draw a perpendicular.
Yes, sir.
These all dimensions are so small that the approximation rule will be valid without any difficulty. And similarly, we drop a perpendicular here. And what we believe that if I this is Q, this is S R T. So from S to S1 and S to T are equal. That's the meaning. Understood?
Yes, sir.
So the path difference is, you can see the S2 path is becoming bigger by value T S2 and S2Q, right?
Yes, sir.
So if you write the path difference, you write the SS1, sorry, the bigger one, SS2 plus S2P minus SS1 plus S1. Now earlier SS2 and SS1 used to get cancelled, but now it will not be cancelled. So this term will have some value. Now the question is how to get SS2. So SS2 is basically TS2 and this is S2Q, isn't it?
Yes, sir.
And now to find the S2Q, we can write the same answer. It will be, because every angle will be alpha only, because once you take one as alpha, there is alpha also. Again, the reason the D dash is much bigger. Okay, so D dash is much bigger than D naught, and D dash and D is much smaller than capital D. So capital D is very standard. It is called the screen and slit separation. So that capital D is always, this. Okay. So now how to find S2Q? So S2, sorry, TH2. So TH2 is basically D sin alpha. Do you realize this is D sin alpha?
Yes.
And H2Q is D sin theta,
Yes.
right? And similarly, as we were changing the sin into tan, we can do the same here also. So we write this D tan alpha. Now we'll make it approximation symbol and D tan theta. And then the tan alpha will give us how much? Then tan alpha will give us,
D naught by D dash.
yeah, D naught by D dash. And this is anyway D Yn by D. Correct?
Yes. Sir. Yes, sir.
Now, if you know this much, then this is more than sufficient to solve any question, because eventually, whatever condition you want to derive, let's say maxima or minima, the process remains same.
Okay.
Okay. So now what will happen? The zero order maxima, where we were getting the zero order maxima earlier in the symmetric case at O.
Yes.
You know what is zero order?
Sir, like the zero.
Zero order. What is the meaning of zero order maximum? I had explained, but once again. Zero order maximum. What is zero order maximum?
Sir, like there is n lambda where like we measure the nth difference. So like when the difference is n lambda, your order will be like the nth maxima.
Yeah,
But then
correct.
here, like the difference in the wavelength is basically zero.
Yeah, it means the both paths are containing equal number of wavelengths.
Yes, sir.
So you have to search for a point in which if you travel through the first route S1 or second route S2, the count of wavelength must be equal. So the difference of wavelength must be zero. That's called zero order.
Yes, sir.
So zero order means the two paths must be optically equivalent. Okay. So the point on the screen at which to arrive from the two routes, the number of wavelength which will face in the path must be equal, or you can say the two paths. So a point on a screen having equivalent optical length via both these slits is called zero order maximum. Okay.
Yes, sir.
Okay. So it's very simple. Let me define it. I think it's good to write it down.
Sir,
Yeah.
I guess
I have
in
written.
last class you
Yeah,
had
yeah.
written it.
Correct. So now what you need to realize, coming back to the O point, if you come from S to O via S1 and via S2, which path is more bigger path? You can
Sir,
see clearly. See, S1, O and S2 are same.
oh, sir, as in like from S to the net path.
Yeah. Now
Yes,
you
sir.
can see that the S2T or TS2 is the extra path.
Yes, sir.
Now, see, let's say if you want to arrive at the old position, the old zero order maxima. Earlier O was the zero order maximum because the S was symmetrically placed and coming there was equivalent via both paths. Now, if I try to come at O, what I am seeing, or you are seeing that the path through S2 is bigger, isn't it?
Yes, sir.
So right now, who is containing more number of wavelengths?
Sir, the path through S2.
Very good. Now, how to make it equivalent? Like which point on the screen will try to make both paths equivalent, below O or above O?
Sir, below, sir.
Very good. So what you need to realize, the moment you shift the source up, the zeroth order fringe will shift downward. So the
Yes.
zero order fringe is no longer at O, rather it is somewhere below. Okay, somewhere below. And now there is a question. They will generally ask you find the position of the zeroth order maxima, because that is a very typical question being asked in the most of the YDSE experiment. That locate the zero order maximum. In a symmetric case, O was the zeroth order maxima. Now O is not the zeroth order maxima. So the question is, what is O? What is the where is the zeroth order maxima? So what we need to realize that zero order maxima is basically a path, a point for which the optical path difference is always zero. And saying that optical path difference is zero is equivalent of saying that the two paths are optically equivalent. Both are same thing.
Yes.
Okay. 22nd November. Just someone is asking me something. Okay. So the zero order maxima is when delta x is zero, and now if you look at that formula delta x, d naught by d dash plus yn d by d. Okay. Now I will make it y0. Why? Because we are talking about the zeroth order position, right?
Yes, sir.
Imagine if you don't shift, this will be zero. And that will lead to the answer y0 is also zero. Correct?
Yes.
But because of this extra term, The why not you will not get at O, you will get at some other position, and the answer will tell you that the answer is negative. Yeah. Do you realize it's negative also?
Yes, sir.
And this is something which already we guessed, right?
Yes, sir.
So we had the idea that this will happen. Understood?
Yes, sir.
So that is the very common idea. Okay, this will happen because that's the only choice. So below the origin, at this distance, below the origin, at this distance, you will get the zero order maximum. Understood?
Yes.
Okay, now the question will be, how many fringe has shifted? So as you lift the source from the point of symmetry, the central bright fringe is shifting down. Okay.
Yes.
So it is like the same, the zebra crossing, but now the zebra crossing has been shifted. So many lines will move, right?
Yes, sir.
So this brighter region may come here. In that process, if this is coming here, then we can say there are 4 fringe movement, right? There are 4 fringe width or 3 fringe width will move, isn't it?
Yes.
1, 2, yeah. So you can say the movement will give you the fringe shifting, like how many fringe got shifted in the due process. As center got moved, the central maxima, sorry, the zeroth order maxima has moved downward. So we say that the fringe pattern has moved downward. It is like if you have seen the projector. Have you seen the projector?
Yes, sir.
So in the projector, you must have seen there is a brightest region, right? And as you swivel the lens, the entire bright part will move up and down.
Yes, sir.
Do you realize is what I'm saying? So the flashlight, let's say the flashlight will have a region of brightness, correct?
Yes, sir.
And any moment will make the brightness shifting on the wall.
Yes.
The pattern will remain intact, but it will shift actually up and down.
Yes,
So the
sir.
question, the general question that you will come across, that how many fringe got shifted? Number of shift in fringes. Like if you want to count the fringes, that how many fringes has shifted, there are 2 possibilities. The fringe shift may be integral, it may be even number, it may be odd number. The fringe shift may be fractional also. Now, if the fringe shift is integral, if you move by 1 beta, 2 beta, 3 beta, 4 beta, then the O will maintain the brightness. Okay, the brightness of the O will remain unchanged, isn't it? It is like I am replacing one bulb by the another bulb. So you are still getting the light.
Yes, sir.
If I shift the fringe by half of the fringe width, so the brightness will be replaced by darkness.
Yes, sir.
If I move by 3 beta by 2, it's still darkness. 5 beta by 2 is still darkness. So odd multiple of beta by 2 will change the brightness from brighter region to dark region. Okay.
Yes, sir.
So the O point which was earlier brighter, the central brightness, because of the shift of the source, that brightness, the central brightness point may become a darker region or brighter region or something in between as well. It depending upon what is the number of shift. Okay. So number of shift in fringes is defined as, you can say, delta n, and delta n we can write very simply by y not by beta, because that we are counting the number, right?
Yes.
So how many beta shift if you want to know how many beta shift, then what you like? Y not by beta, isn't it?
Yes, sir.
And why not? I will like just a value, because I know rest is not of no use upon beta. And if you look carefully, You will realize a lot of things. Theta is what? Lambda d by d. Correct?
Yes.
D gets cancelled. And what you get is d naught by d dash lambda. Correct? And if you remember carefully, d naught by d dash by lambda, what was this value? This is something which you have seen before, right? This is the additional path difference you bring into picture. This is the additional path difference that you derive, isn't it?
Yes, sir.
And what we are dividing with, so this is the additional path difference upon lambda. So this is called the how many extra wavelength you can accommodate in this extra length of path.
Oh, yes.
How to read? It is the extra wavelength I can directly see in that extra path. So if I have developed some extra path, then I can now accommodate more number of wavelength, isn't it?
Yes, sir.
And to know how many extra, rather than doing all this calculation, you can do this directly. That if you know the path difference, which is d naught by d dash, divide by lambda, I will come to know how many extra wavelength I can accommodate now. And now you can say something. You can, comment. What you can comment? You can comment about the nature of fringe pattern at O. So what is the comment on nature of fringe pattern at O? Earlier O was maximum. Now something else will happen. Okay. Question is, to maintain, now this is like two questions. To maintain maxima again, at O, delta n must be an integer. Do you realize this?
Yes.
Which means if the extra path length is having n lambda, the maxima or the central brightness will be maintained. Do you realize this, what I'm saying?
Yes.
So if I want to put this into literature, I can say if additional path difference contains integral number of wavelengths, then brightness at O will be maintained. I hope this is clear.
Yes.
So these are many ways of thinking. So these are the questions, okay, you will come across. They will ask you find the minimum shift to maintain the brightness. Now that's another question. How they ask? Find the
minimum shift to maintain maxima at
central layer. Yeah. So find the minimum shift. Of course, the shift is transverse, right?
Yes, sir.
So minimum transverse or minimum shift to maintain central brightness. So d naught by d dash must be 1 lambda, because the minimum shift is we are able to produce is lambda.
Yes.
Isn't it? You can say put n equals to 1. That's also a simple way of thinking. And therefore, you can see D naught turns out to be D dash lambda by D. Isn't it?
Yes, sir.
I hope this is clear.
Yes, sir.
So how questions are made? Questions are made in this particular fashion. Let's say if you want to replace the central brightness with darkness, so what is the minimum shift required to shift? I mean, change the brightness to darkness, complete darkness. Okay,
Sir, half.
exactly. So that will be half of this value. So it will be lambda by 2. So answer will be D dash lambda by 2D, right?
Yes, sir.
For changing central brightness to darkness, the minimum shift will be how much? For changing central brightness to darkness, the minimum shift in source position, what we can write? D naught by D dash lambda by 2.
Yes.
Okay.
Yes, sir.
And therefore the answer will be D naught equals to lambda D dash by 2D. These all are like questions that you will come across. And I am giving you the question through one of the example. The same thing we are going to repeat. So further, when I'll give you multiple variety of questions, I mean, sorry, the YDSE format, you stick to the basic only. Basic is find the path reference. If they want to know the central maxima, equate to 0. If you want to know the first order maxima, equate to lambda. Second order 2 lambda, nth order n lambda. And if you want to do some maxima to minima, minima to maxima, okay. Also, we have realized that when we were shifting the source up, the fringe pattern was shifting where? Downward.
Downward.
That's the logical. Like if the light, if you turn the light that way, then it will go down. So if I shift the source below, the fringe pattern will shift
Above.
upward. Now, one more thing that I missed in the last lecture, that do we get infinite fringe or do we get finite fringes? Okay. So if you look at the projector light, do you see the infinite light is spread infinitely or it is spread finitely?
Sir, finitely.
So similarly, you will also see that the fringe pattern is also definite or finite. Okay. So now the question is how to count the total number of bright fringe and total number of dark fringe on a screen for a given YDSE. As you have realized that shifting of source can only affect the position, but it will never affect the count. It will never affect the count, isn't it?
Yes, sir.
So what really matters is what is the maximum path difference we can create. Okay. So number of you can say brighter fringe or darker fringe are always equal. And just okay. So the question is how to find the count. Count is very simple. There are two ways. One I will show you mathematically, then I'll show you common sense. Okay. So mathematically, we'll start with count of bright, dark fringes on screen. Okay. Okay. So the question is, on what factor count depends? The answer is simple. Number of bright dark fringes depends on maximum possible path difference. Okay. So if you remember that the way you solve the question is you write delta x equals to n lambda for a maxima, right?
Yes, sir.
So n is what? The path difference upon lambda.
Yes, sir.
That's a logical thing, right?
Yes.
So now if the path difference itself is less than lambda, can we get any maximum, any minimum? No.
No, sir.
So we need some path difference. Okay, so that we can have the number of the count actually. So delta x may be 2 lambda, 3 lambda, 4 lambda, 5 lambda, 6 lambda, maybe fraction also. So depending on the maxima, we only look for the integral part, the integer value, to count the maximum or the minimum. So let's see how we do it. So the n is the count, and that is simple way of writing. In any YDSE experiment, I'll start with a simple one. Tell me what is the maximum path difference possible? And you can guess directly. What is the maximum path difference I can create?
Sir, D.
Exactly. Because from S1, S2, wherever you go, the difference cannot exceed more than D.
Yes.
In fact, we cannot attain exact D here.
Yes, sir.
So we can only attain fractional D. Understood?
Yes, sir.
Now, okay, as I said, okay, we'll proceed mathematically, and then because common sense you have already understood, so we can proceed mathematically. Because for exact D, the point P must be here. Then only you can go from here, and then you can go from here, and then the difference D, right?
Yes, sir.
Which is not going to be possible because in worst case, we can only move on this screen, right?
Yes, sir.
And therefore, this angle theta cannot become 90, isn't it?
Yes, sir.
So that is impossible. Theta cannot be 90. That's logical.
Yes, sir.
So we can add for maxima. Let's count the maxima first, because the count will be same for both. So for maxima, the d sine theta was n lambda. So how much is sine theta?
And lambda by D.
And we know this is always less than
1.
equals to 1. But in this case, it is not going to be 1, in fact, because theta will never become exact 90. So the inequality will hold, not the equality, isn't it?
Yes, sir.
And we are also going to get more than 0 for sure, because negative is not possible in this case, because it's a physical phenomenon.
Yes, sir.
And therefore, if you can just rewrite this particular way, you can clearly see that the n turns out to be how much? 0 to d by lambda. isn't it?
Yes, sir.
And see, d by lambda is something which you have already guessed, that d is the maximum path difference and lambda is the wavelength. So what is the maximum extra wavelength we can contain is d by lambda, right? But in
Yes.
this case, it is less than that. So we need to check that d by lambda is what value. Let's say d by lambda is, so to make you understand, I need to take some numerical value. So d by lambda, let d by lambda is perfect integer is k, where k is 1, 2, 3, and so on. Now, if it is exactly k, then n cannot be equals to k. N must be k minus 1. Isn't it?
Yes, sir.
N must be k minus 1. But the question is, the total number of maxima will be k minus 1 or something else. How many?
So it will be n on either side.
Yeah, it will be k on other side.
Yes.
K above, k below. Sorry, not k. Yeah, n on either side. That's correct. Yeah. So it will be
Okay.
k minus 1 above, k minus 1 below. Okay. And then
Yes.
1 will be the center,
Oh, yes, sir.
because the central brightness is always there, which we overlook actually in general.
Yes.
Because see, here we cannot attain k, so it must be less than k. Okay. So k minus
Yes.
1 is possible. But k minus 1 is possible above the origin, above the O point of the screen, below the O point, and the O itself is maxima in this case. Therefore, the total count becomes how much?
2k minus 1.
Yeah, so 2k minus 1. What was that? So it is 2n plus 1, right?
Yes, sir.
And 2n plus 1 becomes how much? 2k minus 1, isn't it?
Yes, sir.
So this is the count of maximum. I hope this is clear.
Yes, sir.
Now, between every maxima, we have a minima. So if it
Yes,
is
sir.
maxima, so count of minima cannot exceed. It is going to be same. Okay. So if central brightness is there, as we know, let's say if we have a 1, 2, 3, 4 maximum, 5 maximum. 1, 2, 3, 4, 5. I have done one extra. Let me make it symmetrical. Now it's symmetrical, right?
Yes.
And if you count the minima, 1, 2, 3, 4, 5. 1, 2, 3, 4. You can see it's same number.
Yes.
The maxima and the minima will be equal in number. Because between every two maxima, there must be one minima. Okay, so
Yes.
whether you count the maximum or minima, it turns out to be same. So no need to do this a different calculation. You can always count like this. So number of maxima is number of minima.
Sir, what about the zero order?
Zero order is here now. This is zero order. But zero order minima is not possible.
No, sir.
Zero order is always maxima. When you say zero order, if there is no path difference, it is always constructive interference.
Yes, sir. Sir, no, sir, I was asking like number of maxima is equal to number of minima plus one.
No,
Because
no, not plus one. Where is it plus one?
sir, the zero order maxima.
Okay, okay, that way. So, okay, I think okay, we haven't numbered this one, right?
Yes. Sir.
So the counting should start from here only. Just a moment. Yeah, we are going to miss one. So it will be one more. 1, 2, 3, 4, 5. Maxima. Then that maxima will not come. Then we can say there's a one minima here also. But if we say minima here, then count of minima will increase, right?
Yes.
Okay, let's do this. I mean, minima is, then you can see the minima is actually one less, right?
Yes.
Okay, let's do the count for minima. I mean, maybe in this case it is not possible. Other cases are possible. So I'll just keep this on hold. We'll do it mathematically. For a number of minima, it was my intuition that both must be same, but let me see that why it is coming different. Or maybe this diagram is kind of not as per the reality. Quite possible. So for number of minima, because number of Bradford on both sides is bound to be same, apart from 0. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 1. Yeah, I think one difference is there. For number of minima, what we can add? The path difference must be odd multiple of lambda by 2.
Yes.
And therefore sine theta becomes odd multiple of lambda by 2d. And 2n plus 1 lambda by 2d turns out to be less than 1. And 2, and then therefore 2n plus 1 is less than 2d by lambda. So 2n less than 2d by lambda minus 1. So n is less than d by lambda minus half. Correct?
Yes.
And what if we get n as integer? So if n equals to k, not k, if d by lambda minus half equals to k, where k is one, two, three, dot, dot, dot. Let's some integer value. So what we get in that case? So n becomes k minus 1 because the value of n is less than this value, right? So if it is exactly k, if the number is, let's say 10, so n cannot be 10, n must be 9 because n is integer,
Yes.
correct? So number of maxima. But earlier the k was what? Earlier the k was d by lambda. And now the k is d by lambda minus half. So in general, let's call k dash just to compare k and k dash, right?
Yes.
K dash. So k dash is d by lambda minus 1, minus half. And k is how much? D by lambda only, correct?
Yes.
So k minus k dash is 1 by 2. Yeah, so they are not equal. Basically, they are not equal. There is one difference. So if you multiply with 2, it will become 1. So 2k minus 2k dash equals to 1. So 2k minus 1 equals to 2k dash. And that was the answer, right?
Yes.
Okay, it should be equal, but I mean, see, it's a difficult. Why it is difficult to prove it's okay, things will come accordingly because both answer will not be same. The k dash will be different and this will be different. So the
Yes.
number of maxima, it will happen equal only. I mean, the 2k minus 1 is 2k dash, right?
Yes.
And the number of minima, how much we wrote? So number of minima equals to only twice of k minus 1, right?
Yes.
Because see, the minima will be only on the both sides, not at the center.
Yes.
Okay. So number of minima can add as 2k dash minus 1. Okay, this turns out to be 2k dash minus 2, right?
Yes.
This is 2k dash minus 2. That's it. Okay, they're not same. I mean, they're not equal. I mean, but this should not be the case. They must be equal. Why it is difficult to prove? Okay, because we are taking different values of k and k dash, no? Because we don't know whether this term is how much and that term is how much.
Yes.
Yeah. I mean, they are equal. I mean, just remember they are equal. So the number of maxima and number of minima must be equal. Just a minute. Number of maxima. Why I'm getting confused here? Just
So maybe we need to hypothetically consider half a minima above and half a minima below, like the central maxima is divided into two halves, one above and one below. Then they'll become equal to like complete number of fringes to exist when summed up.
Yeah, we need to find the maximum. See, the total number is known to us, right?
Yes, sir.
So total number of fringe cannot exceed d by lambda. And if d by lambda is integer, let's say 10 or 5 or whatever. Okay. So total number of maxima, minima. Why this is happening? Just a moment. Well, this is the maximum. Right? Okay, maybe see, depending on the question, you can derive. I mean, that's easy, but to prove that they are equal, number of maxima equals to number of minima. That's a very nice question. How to prove that they are equal? Because I have also only remembered that these are equal. Never thought about it. Okay. Those two.
Sorry about what I said, like considering half up and half down.
Just a minute. Okay. I think they are not equal. They're not equal.
Okay, so
Yeah. I mean, they need not to be equal in this case. They will be
yes.
equal only in one case. Yeah. So, okay, they're not equal. This point now I can eliminate. But there's one case where they will be equal. So you can just count. Okay. Depending on the formula, the way we derive, you can count actually. Okay.
Okay,
So
so
that's easy. Because we're not supposed to remember anything. But if you talk about the YDC in the second scenario, in which we shifted the source actually. In this case, the path difference is now both sides here also. So we have path difference here, and now this path difference is fixed. Now this we cannot change because alpha is fixed, isn't it?
yes, sir.
You can clearly understand. Alpha we cannot change. On the other side, we can keep on moving upward. So the maximum, the delta x that we can obtain is, for sure, it is d naught by d dash plus dy n by d. That was answer. Okay, and the way we wrote was d sine theta. Correct.
Yes, sir.
Now this will be n lambda. So count of maximum. So just understand the process, that how we derive it. So for count of maximum, we can write as d naught by d dash plus d sine theta equals to n lambda. And then you can add d sine theta equals to n lambda minus d naught by d dash. Okay. So sine theta is how much? And this is less than 1. Again, the same theory. So n
Yes.
lambda by d is less than d naught by d dash, which means the n is less than d naught by lambda d dash. Simply. Understood?
Sir, the second equation, I mean inequation.
Ah, my bad. I just made a mistake here. Yes. Okay, sorry. I just forgot to write the one part. That's why I was thinking, okay, what is happening? So now n lambda by d is less than 1 plus d naught by d dash.
Yes, sir.
So n is less than d by lambda plus d naught by lambda d dash. Correct?
Yes, sir.
So now we have to check for this value, how much is this, whether it is integer or not. And let's see, you can clearly see that d by lambda is extra value, that maximum possible count.
Yes, sir.
And d naught by d dash is the extra path difference upon lambda, which is again extra. So this is the maximum number of difference you can create. Understood?
Yes, sir.
And now you can also remember that the number of fringe above the origin will not be same as below the origin. Why? Because it is shifting below. The
Yes,
fringe
sir.
pattern has shifted downward. So now you will get less number of maxima or minima above the O and more below. Understood?
Yes, sir.
Yeah, so this is how we solve the question of modified YDSE. And they will ask you that how the fringe pattern will shift when you move the source upward. The answer is the fringe pattern will shift
Downwards.
down. So if you shift, I'm just putting here because I don't have a space. So if you shift source above, then fringe pattern will shift downward. That's it. And what is the meaning of shift of fringe pattern? The meaning is the shifting of zero order maxima is called shift of fringe. So wherever the zero order will go, we say the entire fringe pattern has shifted. And these all are the questions that you will face. I hope this is clear.
Yes, sir.
So now I will keep on showing you that how you can solve a variety of modification which you will face in YDSE. Okay. So now there is no source actually. Rather, a beam is coming. You can say a plane wavefront is coming from far away. Okay. Like this. So I can, okay, I will take a different case because I have taken the previous case. So a parallel beam is coming like this. When we show the parallel beam, we never show the source. Source is at infinity, right?
Yes, sir.
Because parallel beam is a property of distant source. Because plane wavefront is a property of distant source, isn't it?
Yes, sir.
So the beam is coming this way, and then after that, it will reach somewhere here. We always do the point, we take the point P above. So just to show you a different scenario, different case, because I have taken the source shifting above. This is similar to source shifting down, isn't it?
Yes, sir.
Because if the source is below, then only light will come like this. Correct?
Yes, sir.
And if you shift the source downward, the fringe pattern will shift.
Yes,
The
sir.
fringe pattern will shift upward, isn't it?
Yes, sir.
So now we can again draw a perpendicular. And S2, S1, T. And this side it is similar theta. And Q. Now, how to write the path reference? That's the only thing. The rest I will not teach. Only path reference. See, up to T, up to this line which I have drawn here, you can see this line. Up to this line, they have traveled equal distance, isn't it? The entire wave has traveled same distance up to this point. Yes or no?
Yes, sir.
So only difference is this, no?
Yes, sir.
So the way of writing the path reference is simple. We write S2P minus TS1 plus S1P. Do you realize this?
Yes, sir.
And now something really interesting happens. S2P minus S1P, we can rewrite, and then I have left with TS1. The moment I see S2P, S1P, I can clearly write this as D sine theta. This is very much known to us. Okay. What about the S2T? How much is S2T? Do you realize this? Sorry, S1T.
S1T is,
You can draw this triangle separately.
yes, sir.
P, S1, S2. Correct? This is D.
Sir,
And the
D cos.
angle, yeah. Angle made by this is alpha. So that is alpha. This is 90 minus alpha. So this is also alpha.
Yes, sir.
So S1T is again D sin alpha. It is D sin only.
Oh, yes, sir.
Do you realize this?
Yes, sir.
So this is D sin theta minus D sin alpha. Understood?
Yes, sir.
It means a point P on the screen, which makes also alpha angle, will have the zero order maximum. If theta equals to alpha, then this is delta x 0, no?
Yes, sir.
So that point represents what? Zero order maximum.
Yes, sir.
So zero order maxima will happen only when the alpha, the theta is equals to alpha value. Isn't it?
Oh, yes, sir.
Do you realize this? Yes or no?
Yes, sir.
So that is the delta x. Okay. So the rest part you can do. For maxima, what you will do? Equate to n lambda. For minima, 2n plus 1 lambda by 2, and so on. So you can find the position of maxima, minima, angular position. So from here onwards, the rest of the journey is something which you will travel. Okay. So I am just showing you the how to find the path reference in different scenario. Okay.
Okay, sir.
So that's why this is called the MYDSE, the modified YDSE. So we are playing with YDSE only. We are making some changes. So in the first case, I had shown you when you physically move the source. In the second case, the source is at infinity and the light is coming this particular way. It can come from the top also. In that case, it will add up. Okay. So yeah, there are many things you will learn actually. I mean, you will come across. The third is, which is now very interesting. Now things are getting interesting here. That's called the effect of media. So I'm going to take the regular YDSE. Okay. The YDSE which we have seen, and then we'll see how the medium can affect things. So we are not going to change anything. So we are going to perform the same YDSE. When I say YDSE, it's a regular one by default. If it is modified, it will be mentioned to you. No need to imagine. All right.
Yes, sir.
And now what happens if I immerse this entire thing in a uniform medium? So I'm keeping the medium uniform here. Now we can play within a medium also, but right now we are keeping the medium uniform. So that's it. The mu is the refractive index of the entire medium. Okay. And now you are performing the YDSE. The light will travel in a similar fashion. correct?
Yes, sir.
And now the path reference will come from only this side, right?
Yes, sir.
As long as things are regular, we can draw like this. I'll show you that when not to draw this diagram. Okay? So there are some like situation corner cases where this diagram will lead to the erroneous answer. So, but as long as things are simple, just keep it like this. Okay.
Yes, sir.
Now, the actual thing is the path reference that we have been talking about was the optical path reference. So the delta x will change the way of writing. So what is the geometrical path? What we write is optical path reference. And what you know is the geometrical path reference, because this S2Q is geometrical reference. It is not optical, isn't it?
Yes, sir.
So the optical path reference is actually mu times delta x geometrical path reference. Okay.
Yes, sir.
So delta x optical is mu times d sin theta. That is the biggest change. Understood?
Yes.
To deal with a very, you can say, generic situation where things are very complex, where medium is varying even from one side of the slit to the other side of slit. So let's say we have a different medium on the left side, then different medium on the right side of the S1, S2. So if things are really complex, if things are changing drastically, then there is a very generic procedure also to solve any equation of YDSE without getting confused. Okay. What is that? So that is called the time equivalent method. Okay. So if you remember the optical path calculation, okay. So I'll tell you what is optical path. So let's say if you go from source to the point P via S1, the time taken will be how much? The time taken to go from, let me keep it capital T1. Time taken by the source to go from S to P. Oh, by the wave via source 1. I mean S1. Okay. So the time will be how much? You can write S1 by speed of light is how much? C by mu.
C by me. Yes, sir.
S1 P by C by mu, because see, you can see that's the beauty. Even if I change the mu, I can write the answer easily, because this method is taking care of every path separately, isn't it?
Yes, sir.
Now, luckily, the mu is same. If I change the mu, still you can write the answer. That's the beauty.
Yes, sir.
And the optical length, optical length 1, OPL1, let's call it, is defined as CT1. That's very simple. So just take the C on the left side. Whatever you are getting is the answer. So your answer is mu times, luckily, SS1 plus S1. Imagine in your mind if it is different mu1 on the left and mu2 on right. So answer will be mu1 SS1 plus mu2 S1P, isn't it?
Yes, sir.
It means it is very, generic procedure that no matter what kind of path they introduce you, you just follow the rule. All variable will take care of itself. So similarly, the optical path length 2 will be how much? And in this case, because it's very simple, I can just write directly CT2, which is mu SS2 plus S2. Am I writing this because it's a very simple situation, right?
Yes, sir.
And therefore, the delta x optical path difference is CT2 minus CT1. That's a very simple way of writing. No need to worry much. And this entire time turns out to be SS2 plus S2P. Now, no matter how complex it may be, you can always write the answer, right? And we know that SS2 and SS1 in this case are equal, so this will become 0.
Yes, sir.
What I'm showing you is the methodology, like how we proceed. And S2P minus S1P is a geometrical value, which we know already, right?
D sin theta. Yes, sir.
Because that has nothing to do with the medium and all, right?
Yes, sir.
So now for maxima, let me just show you for maxima. For maxima, what will happen? The delta x becomes n lambda. So mu d sine theta becomes n lambda. Just I will show you one is like important thing here. So mu d and sine theta is always defined as yn by d, roughly, if you remember.
Yes, sir.
And tan theta is yn by d. We know this, and this is equals to n lambda. Let's keep it equal only. So yn turns out to be how much? No, this is n lambda air. Oh, this is important. N lambda air. We always add the air equivalent, isn't it?
Yes, sir.
So yn turns out to be how much? N lambda not d by mu d.
Yes.
The mu has come in the denominator, which means the yn will come closer to the O, isn't it? So
Yes,
what
sir.
will be the fringe width now? Fringe width is yn plus 1 minus yn, which means the answer will come lambda not d by mu d, which is, you can say, lambda medium d by d. Correct? Luckily in this case you can write. So what you realize that since lambda in a medium is lambda in air, so beta in a medium will be less than beta in air.
Yes, sir.
And with the shrinking size of the beta, what you can say, the fringe width will shrink, right?
Yes, sir.
So in a medium, they will ask you what will be the effect of medium on a fringe width. The answer is it will decrease. So in a medium, fringe width decreases. Okay. Relative to air. I mean, this is very important compared to what? Air or vacuum. Correct?
Yes, sir.
I hope this is clear.
Yes, sir.
So this was the question that you were supposed to answer. Anyway, so we'll come to some more interesting case. So the next part is called effect of insertion of thin lens or thin film, actually. Thin film in front of slit. So these thin films are like the thinnest possible. You can imagine the plastic sheet, you can imagine, in microns. Okay. So thickness of the film is in microns. Do you realize this, how thin I'm talking about?
Yes, sir.
And why it is in microns? Because for interference to happen, the path difference should not be more than coherence length. And micron thickness will introduce extra wavelength. Let's say instead of if in the same path, if we had earlier 5 wavelength, now we may have 6 or 7 wavelength or 9 wavelength. But it will never exceed the coherence length. So we have to make sure that anything which you are introducing, the optical path difference should not exceed the coherence length. Understood?
Yes, sir.
And because everything is happening in the order of wavelength of light used. So we have to be very, very careful about the usage of the thin film. So what we do is we insert thin film of micron thickness. It's a very, very thin film, especially developed. Okay, it is like a membrane of something. Okay, so if you have seen the leaf, and every leaf will have a thin plastic cover called lipids. So if you remove the layer of the lipid, it will come off as a thin sheet actually of micron thickness. So if you have heard about the Teflon coating, have you heard the name Teflon coating?
Yes, sir.
So these Teflon coatings are actually micron thickness coating. So you will not able to see the surface and the coating separately. It looks like the surface one. Okay.
Yes.
So these are like you put a layer of it by a special vapor technique actually. So the same technique is also used for the coating of metal with a different color, different metallic colors. So that's called the vaporization technique. PVD something. Okay, anyway. So what we do is we'll start the insertion of thin film in one of the slit and we'll see the changes. And we'll continue in putting the thin film in both the slit and we'll see the changes. So now I'll go back to my regular YDSE again. And we insert a thin film. Let me insert here on. This is just for demonstration. It is as thin as you cannot imagine. This is called thickness, we call T. And the refractive index we call mu. Okay.
Yes, sir.
So this is your thin film. Let's see how things will change. So we'll continue going back to the point O. So light will enter here, will cross the thin film will reach here, right?
Yes, sir.
Now these thin films are kept not close. It is like put over the screen itself, the opening itself. So there is no gap actually. It's like a thin layer sticking there.
Yes, sir.
In many books, I have seen that they make a mistake. They put the thin film here in that path. That's very, very wrong. Because if I choose a light to go this way, sorry, if I have a light going this way, it will not go through the thin film, right?
Yes, sir.
So that's wrong. This kind of diagrams are inaccurate. They should not do, but nevertheless, they do.
Yes.
Now this is thin film. Now if you go to O, up to S1, S2, I don't see any difference on the left side. Correct?
Okay, sir. Yes.
But
Sir.
if you go, sorry, if you start from S1 to O and S2 to O, geometrically they are same, but are they equal in optical sense? Optically, are they equivalent?
No, sir.
The light will take more time to go from which path?
From S1.
It means optically the S1 is bigger path
Yes, sir.
than S2.
Yes, sir.
So the obvious question is, how big is that? I would like to know what is the extra difference you create, because the path difference geometrically we don't see difference, but optically difference. I would like to know the extra length it creates. So we know that every medium of thickness T and the refractive index mu is equivalent of a vacuum of or air of mu T thickness, right?
Yes, sir.
Do you remember?
Yes, sir.
So optically, if you try to find the path difference, the optical difference, I can write like this. I'll write this way. You can see carefully.
Yes.
S1 O minus T is the air part because this is without medium. S1 O minus T is without medium.
Yes, sir.
And the T is equivalent of now mu T
Yes, sir.
minus S2
Yes, sir.
And you can clearly see this is mu minus 1 ut. Also, logically, you can see how much extra length you have increased. What is the delta x here? It is mu minus 1 ut, mu t minus t, right?
Yes,
See,
sir.
the t length of medium has additionally added a mu minus 1 ut, right?
Yes, sir.
So this path, the other path is mu minus 1 into t times bigger than the path below optically. Understood?
Yes, sir.
This is the additional difference. So the obvious question is how the fringe will shift? Will it shift down or up?
Sir, it will shift up.
Very good. It will shift now.
Yes, sir.
Because we want zero order maxima, it means the path must have equal number of wavelengths.
Yes,
So
sir.
we have to increase the length of the S2 path and decrease the length of the S1 path, right?
Yes, sir.
Because if we decrease it geometrically, the optical increment will compensate. Yeah.
Yes, sir.
So for optical, to compensate the optical increment, we have to decrease geometrically. Correct? This is what you're doing.
Yes, sir.
And that is only possible when the fringe pattern will shift upwards. So we can say the shift will be upward. The central brightness will shift. So when you put the lens in the upper slit, the fringe pattern will shift upward. So lower slit, downward.
No.
Both
Yes, sir.
slit, the tug of war.
Yes, sir.
Okay. Now, if you want to write in general, if you want to just write in general, I'll just show you the general way of writing. Because that is always required. One should always know how to write. This technique remains same. So the path difference, okay, I will just show you the same technique. T1 equals to how to write? How much time it will take to go from this to this? For any complex scenario, stick to this method or common sense or whatever, like it depends on how much you have developed the sense about the wave optics. So many should find this very difficult in the beginning, but if you spend some time, you feel, okay, this is really easy idea. You can actually digest the event very easily and effectively. So T1 is how much? So you will at SS1 by C because there is nothing plus S2P, sorry, S1P minus T is the air part. So again, C, but T is the medium. So I have to tell by C1, correct? So
Yes.
C T1 turns out to be how much? SS1 plus S1P, and then I will add mu T minus T, right? You can write like this. You can see for yourself that the answer is SS1 plus S1P. This is additional difference, right? This is additional to the path.
Yes.
But CT2 will be same because nothing is there.
Yes,
SS2 plus S2P. And then the way of writing is the delta X you can write optical equals to CT2 minus CT1. That's very simple. The same. Always make the sure that you write below minus above. So what is the answer now? The SS2, SS1 will cancel out, right? They are symmetric.
Yes, sir.
So what you get is
mu minus
S2P
1
minus
into
S1P minus mu minus 1 into.
yes.
So d sin theta or dyn by d. And again, you know how to proceed. For zero order, you will just make it 0 and we'll put y0, right?
Yes, sir.
So whatever you want to do from here, you're free to do. I will not come into this. Now, what you can say, again, the same question. Where the fringe will shift, how far it will shift, how many fringe will shift. Every question you can answer without solving any of these because you know that the path has grown by mu minus 1 ut. Just check how many wavelengths we have contributed. Correct?
Yes, sir.
So this is the number of wavelengths that you can contribute extra
Yes, sir.
from the old one, right? Isn't it?
Yes, sir.
So how we do is we always compare with respect to O only. Like earlier when we were going to O, there was no difference. Now going to O will have difference of this value. And we simply count the number of extra wavelengths that we can now accommodate in each path. And this is the number of wavelengths is called the number of fringe shift. And if you multiply with beta, what you will get is called the shift in the zero order maximum.
Yes, sir.
You can always do this mentally. And beta is lambda d by d. So that will cancel out. So yeah, you can do from the basic here, or you can do from here. Choice is yours. Understood?
Yes, sir.
Now, if you insert thin film in the S1, the fringe pattern will shift up. If you insert in S2, then below.
Below. Yes.
So, an obvious question is what will happen if we insert in S1 and S2 both? Then we have to look for which grows bigger. So we'll look for mu1 minus 1 into T1. Then I'll just show you. So So imagine we have a film here and a film here. Of different material, different thickness. So let's call T1. This is nice one. T1, T2, mu2, mu1. So we always go to the O point. We know that while going to O, the path will grow above also, below also. This will grow this much. This will grow this much. And you can just add the condition. So direction of shift of fringe pattern. If the above is bigger than below, upward. If this is less than, downward. And if both are equal, then
No shift.
no shift. Very simple. And then you can find the additional path. You can add delta x equals to, if it is going upward, then you can add delta x additional. And then to find the number of friendship, you can divide this entire value by lambda. That's it. The difference by lambda. Clear?
Yes, sir.
So can you solve any question like this? If you come across a question like this, will it be easy
Yes,
for you?
Yes, sir.
So now you are eligible to solve a large variety of YDSE questions. Okay. Have I shared the YDSE sheet to you? No. Let me
It's
show you.
really Sir, wave optic sheet you have to show.
Yeah. You can see now, I have shared now.
Yes, sir.
Yeah. So like you can start with exercise 1. And we can solve the section A, B, and D. You can try C also. In the modification
Okay.
part, you can also see the E part. F you can leave. Don't solve F. F I haven't taught. Then again, you can go to the other part. You can again start solving, and you have to start solving to realize that these are very easy.
Yes. Sir, polychromatic light.
Means multiple wavelengths are used simultaneously. So one wavelength will have its C. The fringe pattern we define for each wavelength. Okay. So let's say lambda 1 is making maxima somewhere, then lambda 2 cannot make maxima there only, correct?
Yes, sir.
So to find the actual maxima, if let's say if I use dual chromatic light, only 2 colors are there. Okay. So let's say we have a
Yes.
red and blue. Oh, yeah, red and green. Okay. So the fringe pattern of red will be different than the fringe pattern of green. And on screen, we cannot see both. We can see only the difference. Understood?
Yes, sir.
Now the brightest part of the screen will be where both will have the common maximum.
Okay, sir.
So we'll assume, let's say the nth order of green and the mth order of red are coinciding. Okay. And then we find some relation. So I'll do this in the next lecture. Okay, for sure. So as of now, I can leave. We are going to cover everything. The reflection part I have covered, but since you need to see at least one question, then you can solve the reflection based question as well. So that will be covered in the layers mirror. And then we have Fresnel biopage that will cover the remaining part. With that, we'll cover half of the wave optics. Then we'll go to the diffraction, polarization. That's it. These two things are there. Then this will cover at least 2 to 3 questions in the JEE-Mains and NEET. 2 to 3 questions. In fact, more than that. Not just 2, 3. I think it will be more now. Coming years, you can see, I mean, in 20 to 23, I think I am expecting more questions from these topics. The
Sir,
future.
wave optics itself.
Yeah. In mains, they ask a lot actually. Wave optics means one question from interference, one from diffraction, one from polarization, one from the polarization by reflection. So these are like 3 to 4 questions which you can expect. Also
Yes.
in the examination, like bits Pilani, they ask in fact much more than 3, 4. They may ask 4 or 5. And why these chapters are important? Because many students they don't give importance to these chapters. The reason is in most of the coaching it is taught in one lecture. You won't believe. In 99% coaching institutes, wave optics is completed in 1 to 2 lectures. That's it. It is not possible to comprehend in 1 to 2 lectures.
Yes, sir. So they ask more conceptual questions on these, sir.
Yeah, very conceptual. Like everything which we are discussing will come in examination. Like
Yes,
how the effect of shift of source will affect the fringe pattern, how to count the wavelength, what is the meaning of zero order maxima, how to replace the central maxima with another maxima by creating the the modification in YDSE. So unless someone is not understanding completely the entire theory, what is exactly happening, it is very, very difficult to answer it. Although it's a one-line solution, most of the YDSE questions are solved in 1 to 2 lines, maximum 2 lines. But to write that 2 line, you need to know a lot. Okay.
Okay, sir.
So you can start practicing. As of now, I think I would say you can start with SC Verma because SC Verma is also very good. Then I'll take care of the rest other concepts. Okay, so it's a big chapter for me. I teach in 6 to 7 lectures minimum.
Okay, sir.
I will be covering things in detail because it's a very important, crucial from the point of view of scoring in examination. So these are like 100% guaranteed marks in the examination.
Okay, sir.
The only thing which is not guaranteed is, you can say, thermodynamics. Sometimes becomes really difficult for student. Sometimes easy. What is not guaranteed is rotational. Sometimes it is easy. Sometimes it is very difficult. But wave optics, properties of matter, these chapters are like guaranteed questions. Like you can always solve if you know just the basic. Okay.
Okay, sir. Yes, sir.
All right. So see you in the next lecture. And we'll keep see your timing is not getting, I mean, fitting in my schedule. So you have to change the time. Come sometime in afternoon. Then only we can spend more time, and then we can finish in one go.